That's Dre's Tutoring. Hey guys, welcome to today's video where we'll be going over Boyle's Law. If you guys haven't already checked out the last video talking about gas properties, make sure you guys check that out before getting to this video, because what we talked about in the last video is gas behavior. Now what we're doing is we're combining some of the characteristics of gases like temperature, volume, and pressure. But for the sake of this video, we're talking about Boyle's Law, where the relationship will be between pressure and volume, as you guys see here. So the main takeaway that you want from this video is that pressure and volume can change each other, right? And I'm trying to use baby terms here, okay? You know how we do on this channel. Meaning, as the volume increases, the pressure decreases. And then as the volume decreases, the pressure increases. Now I'm going to go into more depth about this. This is kind of just the title page where I just briefly go over stuff. So if we go over to our right, one thing I do want to get out the way are the different units that we use for gases. We're all familiar with ATM, which is atmospheric pressure, mmHg, torr, Pascal, torr, and so on and so forth. And these are all different units that we use when measuring gases. And you'll see in some examples that I use where we may have to use a bit of conversion there. But the main takeaway here is that all of these are equivalent to 1 ATM or 1 atmospheric unit. Okay, so Boyle's Law. Let's go over pressure real quick. Pressure is when particles hit against the walls of a container and they exert pressure. In the last video, we talked about this favorite container word that I use a lot, where we'll have a particle of gas, and gases like to be far apart from each other. You know, it's very different from liquids and solids. So we have these gas particles, and they're, they have velocity, they're roaming free, running like crazy in this closed container. And what will happen is they'll hit the walls of this container, and pressure is exerted. And so there's many particles that do this in the container as they hit the walls, exerting something called pressure. Volume is the amount of space that a substance or object occupies. So within this container is a certain volume. So let's just say the volume of this container is 4 liters, I guess. And compare it with another container that it's a closed container and just may be 1 liter, and we have the gases here. Because the volume is lower or less, you can expect a greater pressure in this container than the one with 4 liters, where it'll have lower pressure. Okay? So now let's go more into Boyle's Law. This is probably the most important slide as far as the concept. So pressure and volume is Boyle's Law. These are the two characteristics that we'll be caring about, pressure and volume. Now, how about temperature? For the sake of this equation, temperature is constant. And we'll see in other gas laws where we combine volume, pressure, and temperature. So as I said before, as the volume decreases, meaning that the volume of that container is lower, pressure is increased. As the volume increases, the pressure decreases. So if we look at our photo here, and we can just ignore these two. I only use this picture because I liked it so much. We'll look at this middle where we have Boyle's Law. And it says volume decreases, wall area decreased equals increased pressure. So if we look at this left one where it's the baseline, we can see we have gas particles in a closed container. But as we press this piston down, the volume is decreased. And since the volume is decreased, particles are hitting these walls and pressure is exerted rapidly. So therefore, the pressure increases. volume and pressure are inversely proportional. And this is just a fancy way of saying if changes occur in one property, the other property changes as well, right? And we see that up here, where if one thing changes, the other has to change. So if the volume increases, the pressure decreases. And if the volume decreases, the pressure increases, and vice versa. So if the pressure goes up, that must mean that the volume is decreased. They're inversely proportional. You know, if one change occurs in one property, the other will change as well. And I do have in stars that temperature is constant, which is one of the most important things, one of the most important things to consider when looking at Boyle's law. All right, so Boyle's law can be shown as this equation here, where P1 V1 equals P2 V2. And we don't ever learn this stuff until really going into examples. So I have two quick examples that we'll go over that you guys will see on tests in some of your exams. So again, they're inversely proportional. So what I have here is condition 1, condition 2, the know, and predict. Now, what does this all mean? In these word problems, you're typically given the initial. In mathematics, you're usually given the initial in word problems. The initial, or condition 1, is the P1 and V1. The condition 2 is the P2 V2. The know is this side, what they're giving you. And then the predict is what we think will be the result, okay? Actually, in condition 1 and 2, sometimes this can be a question mark. We don't know what it is, and that's what we're looking for. And that's where we would have to isolate that condition or that variable. So let's look at some examples. The first example here, we have a sample of hydrogen gas has a volume of 5.0 liters and a pressure of 1 atmospheric. What is the new pressure if the volume is decreased to 2.0 liters at constant temperature? Well, let's go to our condition thingamajigger that we have here. So if we write out condition 1, condition 2, the know, and then the predict. And we don't always have to do this. I just think it's a little help for people who are introductory mathematics and things like that want a quick and easy way to try and learn how to isolate variables and solve for different variables, because this is something I had a lot of issues with word problems. So condition 1, what are we given? A sample of hydrogen gas has a volume of 5.0 liters. So let me just write out our equation here, where it's P1 V1 equals P2 V2. So they already give us the first volume. The first volume is this 5 liters. So we know that V1 equals 5.0 liters and a pressure of 1.0 atmospheric unit. Oh, would you look at that? So they gave us the initial volume and they gave us the initial pressure. So P1 equals 0 atm. What is the new pressure? The new pressure if the volume is decreased to 2 liters. So now for our V2, V1 and V2, V1, the V1 is, the V2 we know is 2.0 liters because that's what's given. It says it's decreased to 2 liters. What we don't know is the second pressure because it says what is the new pressure. So that one we don't know. So what else can we get from this problem? We know that the volume decreases. And what is our prediction? If the volume is decreasing, what will happen to the pressure? Remember, if the volume decreases, that means pressure increases. So our prediction will be that the pressure will increase. So if we get an answer that is lower than 1 atmospheric unit, we know we did something wrong because it has to increase. So we know that they gave us the volume, 5 liters. They gave us the pressure, 1 atmospheric unit. We don't know what the new pressure is. We don't know. But we know it decreased to 2 liters. and our prediction is that the pressure will increase. So if we go ahead and plug this in, we have P1 V1 equals P2 V2. All right, so remember, what are we looking for? We're looking for P2, so we have to isolate that condition or variable. So how do we do this? Well, we would divide by V2 so we can have some cancellation go on, right? So then we can cancel out this guy. And what we have left is P2 equals P1 V1 over V2. Now we can do the plug-in game. So we know that P1, we know that P1 equals 1.0, and we know that V1, or the initial volume, is 5 liters. So we could go ahead and put 5. And it would be smart to put the units there as well. And actually, I'll write it out like this for you guys so it's easier. 0.0 ATM. There we go. And now what is V2? That's correct. V2 is 2.0, right? So we'll put 2.0 liters. And now what we can do is we can cancel out like variables. And if we punch this into our calculator, we can get that P2 equals 2.5 atmospheric units. And this is our answer. And again, it's 2.5 atmospheric units, and it has increased. Because remember, we know that the volume decreased, and since the volume has decreased, that the pressure must increase. All right, so we used our P1 V1 equals P2 V2. We got rid of some of our conditions, and we're left with P2 P1 V1 over V2. And we can just go ahead and plug in our units, cancel, punch in our calculator, P2 equals 2.5 atmospheric units. Okay, on to our second and last example. The gauge on a 12-liter tank of compressed oxygen reads 3,800 mmHg. How many liters would this same gas occupy at the pressure of 0.75 atm at constant temperature? And they even give it to you in this. Remember, the temperature is always constant. So what we can do here is we're going to look at this. Where is it? This 3,800. We have a volume here, and then we have the 0.75 atmospheric units. So let's go to our conditions. So condition 1. So we're given our pressure, right? It reads 3,800 mmHg. So we're given the first, or the initial pressure, which is 3,800, right? The volume we're given, the initial volume is 12 liters. So we could go ahead and put that in our condition 1 as well. Okay. Condition 2. We are looking for the second volume because it asks how many liters, which is a measurement of volume. How many liters would this same gas occupy? So we're looking for V2. That is what we're looking for. Our P2, what's the second pressure that we're looking for? Well, it says how many liters would this same gas occupy at a pressure of 0.75 atm or atmospheric units. So this would be our second pressure. Now, there's something very interesting about this. To keep the same units together, because we have mmHg here and 0.75 atm, we have to match the units. In our last example, it was at 1 atm, and we found it in atmospheric units as well. But for this example, we have two different units that we're using here. We're using mmHg and atm. So we're going to have to convert this. And if we look over at our chart, we know that 1 atm is equivalent to millimeters of mercury, 760. So all we have to do is go ahead and convert this. So the way we'll set this up is we'll do 0.75 atmospheric units times 760 millimeters of mercury over 1 atm, because 1 atmospheric unit is 760 mmHg. So now what we could do is cancel our like units and then just multiply across 0.75 and 760, and we get 570 mmHg. Okay, so what now we can write for our P2, we can write 570 mmHg. Okay, so now how about our know? What do we know? What do we know? So if we read this again, the gauge of 12-liter tank of compressed reads 3,800 mmHg. How many liters would this gas occupy at a pressure of 0.75 atm? So we're going from 3,800 mmHg to 570 mmHg. So what we know is that the pressure will decrease because this pressure is lower than this. And how about our prediction? So since the pressure is decreasing, we can assume that the volume will increase. Okay? So now we can finish this up by going ahead and doing our P1 V1 equals P2 V2. We're isolating the second volume because that's what we're looking for. We're looking for this second volume. So let's go ahead and do that. And how we'll do that is we will get rid of the P2. So now we're left with V2 equals P1 V1 over P2. And now we can just do our plug and play where V2 equals P1 V1 over P2. So we can do our 12 liters times our first pressure, which is 3,800 mmHg, over our second pressure that we got, which is 570 or 570 mmHg. Okay, and if we multiply this across, first divide, multiply across, we will get 80 liters as our answer. Okay, so how many liters would this same gas occupy at a pressure of 0.85 atm at constant temperature? The answer will be 80 liters. Okay, so this was just a quick video going over Boyle's law and some examples that you guys will see. I really want to stress the importance of conversions where everything here is equivalent to 1 atm. So really read the problems and see where you have to make the conversions. Make sure you guys set it up where you show the different conditions, what you know, and what the prediction will be, because it really does help you in the long run. Then, of course, you just isolate those conditions or variables and cancel out, and then just do your plug and play. Okay, so that concludes this video. Let me know if you guys have any questions, and I'll see you guys next video. Peace.